Hi. I'm so excited to be here. I flew here yesterday from California, flew Ukraine International Airlines. It's great. This is a great city. I've been wandering around my first time in Ukraine. It's delightful. My name is David Silver. I lead the self-driving car team at Udacity. Udacity is an online education company in California and Silicon Valley. We teach classes in a wide variety of topics, mainly related to software engineering, and I lead our self-driving car program, which trains software engineers to work on autonomous vehicles. So I'll talk with you a little bit today about how our self-driving car works. We have a self-driving car at Udacity, and a little bit about how self-driving cars work generally through the lens of the projects that our students do as part of the self-driving car nano degree program. First, though, I would like to teach you something. I would like to teach you how to be an actor. I am a software engineer, but because I teach online, I spend a lot of time now in front of a video camera recording lessons for students to watch all around the world. And so Udacity, my company, has spent a lot of money trying to turn me from a software engineer into an actor, and I would like to teach you how to be an actor. So in order to do this, I'm going to show you what we do every day before we get on camera. So if you can stand up, 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 up. All right. So the game here is we have 4 limbs, hand, hand, foot, foot, and we're going to shake them out 8 times, then 4 times, then 2 times, then 1 time. All right, you ready? So hand up, ready? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 1, 2, 1, 1, 1, 1. All right. Okay. All right, we're going to get going. It's going to be a great day. Okay. I have been at Udacity for about 2 years, building our self-driving car program and some other classes that we teach. I came to Udacity from Ford Motor Company. I worked on their autonomous vehicle team at Ford in their Palo Alto office, right next to Stanford University in Silicon Valley. And before Ford, I was, for many years, a normal Silicon Valley web software engineer. Does anybody know what that red icon is there? Ruby. I was a Ruby on Rails engineer for about 10 years. I worked on web software in Silicon Valley. And a few years ago, I got really excited about self-driving cars, but I didn't have any background in automotive software or robotics. And so I started taking classes online at Udacity and other places, and eventually I was able to join the autonomous vehicle team at Ford. And the folks at Udacity saw that and said, why don't you come to Udacity and build out for other people essentially what I had done for myself, a path to working on self-driving cars. So we've been doing that for the last 2 years. About 12,000 students all around the world have signed up for the self-driving car program. Many of them now work for on autonomous vehicle teams at automotive manufacturers, automotive suppliers, ride-sharing companies, and all sorts of other suppliers and companies in the autonomous vehicle space. So it's been a delightful journey. Udacity is a particularly interesting company to do this work at because Udacity was founded by a man named Sebastian Thrun. Does anybody here know Sebastian or know of Sebastian? Anybody? Yeah, okay, so a few people know who Sebastian is. Sebastian is, in a lot of ways, the father of the self-driving car. He's originally from Germany, from Cologne. He was a professor of computer science at first Carnegie Mellon University and then Stanford. And he led the Stanford University team that won the DARPA Grand Challenge, which was a big 100-mile self-driving car race through the California desert that really kicked off the self-driving car boom in 2005. He left Stanford and went to Google, where he founded the Google Self-Driving Car Project, now known as Waymo. He led that effort for about 8 years. And then he left Google to go back to education and build Udacity to deliver Stanford-level education to anybody anywhere in the world. And so it's been a real honor and delight for me to get to work with Sebastian, not only on education, but on self-driving car education specifically. And I've learned a lot from him, and the course has benefited tremendously from being able to get guidance from Sebastian on how self-driving cars work. So I mentioned we have our own self-driving car at Udacity. Her name is Carla. Carla is a Lincoln MKZ, essentially a fancy Ford Fusion. And we purchased Carla from a company called Autonomous Stuff. Autonomous Stuff takes cars and makes them drive by wire. So not necessarily self-driving, but so that you can control them electronically. In fact, they brought Carla to us. She wasn't named Carla at the time. We named her Carla, but they brought us a car, and they gave us a video game controller, a PlayStation controller, and said, look, you can drive the car with a PlayStation controller. And in fact, we could, and it's really something to drive a car with a video game controller if you've never tried that before. But they said, if you can drive it with a video game controller, you can program a computer to drive it. Now it's your job to program the computer to drive it. And so we spent about 5 months programming the computer to drive Carla. And in fact, we got Carla to drive from our office in Mountain View all the way to San Francisco. That's a distance of about 50 kilometers. We had a goal to drive Carla up the main street, the main commercial street of Silicon Valley, El Camino Real. And we did that a couple years ago, and we've been working with Carla ever since. So I'll tell you a little bit about how Carla works and about how self-driving cars work generally, and a little bit about some of the projects that our students do as part of the self-driving car nano degree program at Udacity. So who here knows how self-driving cars work, works on self-driving cars? Anybody? All right, a few people. All right, so this is our self-driving car, which may work differently than your self-driving car. And this is Carla driving up El Camino Real in Silicon Valley, and you can see a lot of different things going on here. And as we go through an explanation of how Carla works, we'll talk a little bit about how each of the things on the screen is happening and what they mean in relation to Carla driving down El Camino Real going from Mountain View to San Francisco. So I think of self-driving cars as having 5 key components: computer vision, sensor fusion, localization, planning, and control. Computer vision is how we use cameras to see the world around us and understand the environment. Sensor fusion is how we use other sensors like radar and LiDAR to augment our understanding of the world that we get from cameras to build a more complete understanding of how the world looks and how it works. Localization is how we figure out where we are in that world. And then planning is how we decide the route that we want to take through the world to get to where we want to go. And the final step is control, which is how we actually turn the steering wheel and hit the accelerator and hit the brake in order to move the vehicle through the world along the path that we developed in the planning stage. So those are what I think of as the 5 key components of autonomous vehicles. And the first is cameras. And so in fact, you can see the camera image here of Carla driving down El Camino Real. And mainly what we're doing with the camera image here is traffic light classification and detection. And so in fact, you can see a tiny little image of a traffic light there. And we are using the camera primarily to detect, is the traffic light red, yellow, green, where is the traffic light? Because this is a pretty simple drive. We're staying in our lane. We're doing a lot of the other intelligence that Carla needs in order to drive. We're using other sensors for that. The principal thing we're using with our camera right now is for traffic lights. Other self-driving cars will combine camera data with LiDAR data and radar data in order to understand where objects are. For our car, which is a relatively simple car, principally we're using our camera for something like detecting traffic lights, traffic signs. So how do we even do that? Even just detecting traffic lights is not so straightforward. We use something called a neural network. Have folks here worked with trained deep neural networks, heard of deep learning as a concept? few people. So deep learning is a relatively new type of artificial intelligence. It's been developed in the last 5 or 6 or 7 years into something that's really transformed the field. And it's inspired by biology. And so you can see on the slides up here, on the left, we have this thing called a perceptron. That's the fundamental unit of an artificial neural network. That's what the computer is doing. We're taking these inputs on the left and feeding them into a central node that calculates an output. And on the right, we see kind of the biological equivalent or inspiration for how deep neural networks work. And this is a neuron, and the neurons have these things called dendrites and a nucleus, and then an output called an axon, which fires a signal. So the dendrites bring in signals from other neurons. The nucleus decides whether or not to emit a signal, and then the axon carries that signal, if it's emitted, onto the next neuron. And you can see they kind of resemble each other. They have these inputs, they feed into a central unit, and then the central unit feeds an output further along the line. And in fact, if you chain together enough of these artificial neurons, you can get a network. So this is a pretty simple network. It's a 2-layer network. The bottom layer is input. And then the next 2 layers, those are the actual neural network. The input feeds into a couple of neurons in this hidden layer in the middle, and that feeds into an output layer at the top. And this is really simple, but you can imagine stacking these neurons together into much more complex units. And in fact, you can stack thousands and thousands of these units together and get what are called deep neural networks. And this is what's known as deep learning. And the way deep learning works is you feed data into the bottom of the network, and that data propagates up and ultimately produces an output. We've represented the output as this neuron at the top of the network here. But the really neat thing about deep learning is that it's able to learn from data. And in fact, the way it does this is it feeds input into the bottom of the network, calculates an output at the top of the network, and then compares that output to what's called a ground truth value, and figures out how wrong am I, basically, or how correct am I. And it uses the difference in what it calculates and what the real truth is, and then it sends that data backwards through the network through a process called backpropagation, and adjusts all the little weights and all the little neurons and connections between the neurons. And if you do that process forward and backward, thousands and thousands of times, eventually the network learns over time how to do something like classify a traffic light, whether it's red, yellow, or green, or even detect where the traffic light is. So this is an animation of how backpropagation works. You can see we're feeding input into the bottom of the network. It's propagating up through the network, and then it calculates a value. So it calculates what might be called an output value, and what we do is we calculate the error, or epsilon, between what the output value of the network is and what the actual truth is, the ground truth value is. And then the next thing we do is we send that error backwards, back through the network. And at each stage in the network, we're adjusting the weights, we're adjusting the numbers in the network based on what the error was, so that over time our network converges closer and closer to the truth. And this is basically how deep neural networks work. But of course, this is pretty simple, and you might wonder, how do we take an image, say, of a traffic light, a camera image, and feed it into something that looks like this? Well, in fact, you can build much deeper and even slightly different structured deep neural networks. This is a visualization of something called a convolutional neural network, which has really become the main way that companies work with camera images, or researchers or engineers work with camera images, is you feed the camera image into the back of this neural network, and then the information propagates forward through the end, and eventually you are able to build a classifier and classify whether a traffic light is red, yellow, or green. So that's how deep learning works. That's how we work with our camera in Carla. We've trained a deep neural network to detect and classify traffic lights. But there's lots more to self-driving cars than just cameras. What you can see here is an image of us driving down the road, not in El Camino Real, the commercial street, but on one of the highways in Silicon Valley. And you can see a couple of things going on here. You can see lane line detection going on, and then you can see drawing bounding boxes around other vehicles. And in fact, this is one of the projects. One of our students built this as part of the self-driving car nanodegree program. Students learn to train deep neural networks to recognize objects and other vehicles on the road, and you can see a couple vehicles passing each other, and the neural network is trying to figure out, is this one car, is it two cars? And this is actually pretty close to what you might actually see in a production level computer vision system on the road today, and it's kind of amazing that students can do this in the first 3 months of the self-driving car program. There are just a lot of tools out there related to computer vision and deep learning to take advantage of and build on the shoulders of work other people have done. So that's how cameras work, if we want to just think about how to understand the world through cameras. The next step is sensor fusion. So how do we fuse sensor data together to understand how the world works in a deeper way? So cameras are great. They're particularly great for things like classifying traffic signs and traffic lights. They are less great for things like depth perception. How far away is a vehicle, or how fast is it going? They also don't work as well at night, of course, because you have to have headlights, and there are other sensors like radar that function really, really well in the dark, whereas cameras are not as strong. So we use other sensors to build a complete picture of what the world looks like. And in fact, Carla has a whole suite of sensors. We have a camera, actually an array of cameras. We have radar, we have LiDAR, we use GPS. Other self-driving cars might even use other sensors. They might use IMUs, inertial measurement units, to track how far the vehicle's gone. They might use thermal cameras. There are all sorts of sensors that self-driving cars use. But the three big ones are cameras, radar, and LiDAR. And in fact, here's an image of what those look like on our car. We use a point gray camera, or a rack of point gray cameras that are attached to the windshield of the vehicle. We have Delphi ESR front-facing radar that's embedded in the bumper of the front of the vehicle and looks forward to detect objects in front of the car. And then we use a Velodyne LiDAR. We have an HDL32 LiDAR, which is what you see here. We also have a VLP16, a 16 beam and a 32 beam LiDAR, depending on the circumstances. We'll typically attach one or the other to the roof of the vehicle. And a LiDAR is essentially an array of lasers that emits beams and then catches those beams when they bounce back, and uses that to create a point cloud of the environment. So once we have all these sensors fused together, we can do all sorts of different things in the perception layer of the vehicle. So we can do lane detection, traffic light classification, traffic sign classification, object detection and tracking, free space detection. Different cars do things in different ways. So for example, in Carla, we don't do a lot of free space detection, but a lot of self-driving cars now, in fact, are looking not just at where other objects are on the road, but in terms of what free space is out there, so that they know where they can navigate safely. So if you go back to this, if we go back to this image of, or this playback of Carla driving down the road in California, you can see a lot of different things going on with the sensor suite here. So the black overlay that takes up most of the image, this is the LiDAR scan. These are the laser beams that are being emitted from the sensor on the roof of the car. And what you can see are a few things. You can see a white background here. That white background is the map. That's the high definition map. It's the type of map, say, that a company like Here would make. In our case, we made it ourselves. And then you can see these red concentric circles, and those red concentric circles are the laser beam that the car is actually sending out. And you can see how those red concentric circles are centering on our actual car. And you can see other vehicles coming up behind our car, and you can kind of see what they look like in the laser beams. And then as they pass our car, you can see our front-facing radar start to pick them up, and that's when those vehicles turn into these blue and white rectangles. That's the fusion of both what our LiDAR sees and also our front-facing radar. And then, of course, you can see the blue trajectory and the green trajectory in front of the vehicle. And so this is how we use a combination of different sensors: the camera for doing things like traffic light detection, the radar for picking up objects in front of us, and in fact, mostly what we're using the LiDAR here for is to localize ourselves to the map, which we'll talk about in just a second. So localization. Localization is how Carla or any self-driving car figures out where it is in the world. And you might think that that's pretty easy because we all have cell phones now and they all have GPS in them, and so we all know where we are most of the time. But in fact, GPS is only accurate to within about 1 to 2 meters. And if you think about how big 1 to 2 meters is, if a car is wrong about where it is by 1 to 2 meters, it could be off on the sidewalk hitting things. And that would be really, really bad. So we have to use much more sophisticated techniques in order to understand precisely where we are in the world so that we're never off in a different lane or off on the sidewalk or someplace that we shouldn't be. So this is how localization fits into the self-driving car stack. We feed our LiDAR data into a localization block, and we also have a map that feeds into that localization block. And the combination of the LiDAR scan and the map, we combine those together and we use that to figure out precisely where we are on the road to single-digit centimeter level accuracy. So if you imagine a car driving through a city, imagine we're the yellow car in this picture and we want to figure out where we are. We could start with GPS, we could take a satellite signal, but of course, as we discussed, GPS is only accurate to within about 1 to 2 meters. It varies. In open road, it can actually be quite accurate down to about 10 centimeters, but in an urban environment with lots of tall buildings, the satellite signal gets more noisy, and in fact it can be even less accurate than 1 to 2 meters. And so we have, say, this red circle around the vehicle. We could be anywhere in that red circle and we don't know precisely where we are, and so we need much higher definition localization. And so how do we do that? We use a map. And so you can imagine a hypothetical map where we have precise information about lots of different landmarks. And as we're driving our yellow car through the city, our lasers are scanning where all these different landmarks are and comparing what we see to the map. And by doing what is essentially a really sophisticated form of triangularization, comparing where all these different landmarks are relative to the map, then we can figure out where we are within the really precise single-digit centimeter level accuracy that we need. Now, what we see here with these different landmarks, these landmarks could be, say, light posts or mailboxes, or even the curb on the side of the road. This is what's called sparse localization. So we have a sparse set of things, a light post or a mailbox, that we're comparing ourselves to. In fact, what we use with Carla is what's called dense localization. And so instead of different landmarks, what we actually have is a whole dense LiDAR map. And that's the white map that you can see on the black background here. And the red circles, as I mentioned, that's the LiDAR scan. Those are all the beams coming out from the laser on top of the car. And we're comparing what those red laser beams see to the white map, and by doing really sophisticated triangularization, we can figure out precisely where the vehicle is. So that's how we localize the vehicle, and in fact, that's a lot of the work of driving Carla down the road, is we've mapped this area precisely, and then we're comparing where we're driving to the map. So now that we know what the world looks like and where we are in that world, the next step is to figure out how to get where we want to go. So with Carla, this is pretty straightforward, actually. With Carla, we mainly drive Carla by hand somewhere, and then we train Carla to follow the path that we already drove by hand. But of course, with more complex self-driving cars, like the type that are getting tested by companies like Waymo and Aptiv and Lyft, those cars need to be able to go in arbitrary places that a human driver has never specifically trained the car to go. They need to be able to make decisions about how to drive through the world. And the way they do that typically involves a number of different steps. So you can see in the planning block here, that red planning block, we start with route planning, and that's kind of the global level planning. It's like, how do you get from here to a different part of the city? And in fact, a lot of times we can rely on other tools, something like Google Maps, to help us figure that out. The much harder part are the next three pieces. Prediction, that's how we predict where other vehicles on the road are and what they're going to do. And then behavior planning, and that's how we figure out what we want to do in response to what other vehicles are doing, and also where we want to go. And then the final step is trajectory planning. So once we know what we want to do, say, do we want to turn left? Do we want to go straight? Do we want to speed up? Do we want to slow down? We need to actually build a trajectory to execute that behavior. So if we start by thinking about, If we start by thinking about prediction, imagine we're here at an intersection and we're the blue car, we're a blue self-driving car, and we want to figure out where the green car is going. We don't really know, right? The green car could be doing a number of different things. We might have a model that says the green car is probably going to either go straight or turn right. Probably only a couple of options here, although in more complex environments, there might be a number of different things that green car might do. And in fact, we might use something like a neural network or data-driven decision-making to figure out exactly what we think the car is going to do, and over time, get a better and better understanding of the probability of what that green car is going to do. And we have to do this, of course, for all the different vehicles on the road. It's simple enough to do this for one green car, but if we're driving in traffic through Kiev, there might be lots of different cars around, and we have to predict what each of them are going to do in the future. And maybe there are different things they might do, and we have to have probabilities for what any given car might do at any given time step, and it becomes really dense and a much more complex problem. Even then, once we know what other vehicles on the road are going to do, or once we can predict with some probability what they're going to do, the next step is to figure out what we want to do. And there are a lot of different ways to do this. Path planning or behavior planning is a little bit like the Wild West of self-driving cars. Everybody's trying to figure out the best way to do it. This is a particular technique that we learn from Mercedes-Benz. It's called a finite state machine. Essentially, you have a bunch of different states. We are in the keep lane state here right now. We're the lane keep state. It's the blue circle with the red ring around it. And imagine, again, we're the blue car. We're out on a highway. We're coming up on some cars in front of us that are slow, and so we want to shift lanes and get around those cars. So what do? The first thing we do is we might actually shift to a new state that says prepare for a lane shift. So we turn our signal on so that the other cars on the road can see that we're signaling for a lane change, and we start to slow down. We look for a gap. We see that gap in the left lane, so we slow down so that we can fit into that gap. Then the next thing we do is we shift states again, and we actually perform a lane change, and we move into the lane change state. So now we're in the lane change state, and we've successfully shifted lanes. The next thing we would do is shift back into the lane keeping state, and we'll stay in the left lane as we pass the cars in front of us. This is a pretty straightforward finite state machine, and it works pretty well for highways. Things get a lot more tricky when you're in an urban environment because there are just so many more options for what you might do. Highway driving is pretty easy because it's so structured. There are only a few different things you can do. In urban driving and city driving, things are a lot less structured, which makes behavior planning a much more challenging problem. But imagine we figured this out. We figured out behavior planning. We know what we want to do at any given time step. The next thing we have to do is figure out a trajectory, build a trajectory to actually execute our behavior. So imagine we've decided we want to shift lanes left. We still have to actually build a trajectory to do that lane shift. And there are a lot of different ways to do this as well. Some of them rely on mathematical optimization. Some of them, like this image here, rely on what's called sampling. So we might look at a bunch of different possible trajectories, and that would be the sampling step. We look among each of them and we score them, and we say, what's the best trajectory? And by scoring them, we can figure out the optimal trajectory of the, say, 10 or 15 or 20 trajectories we sampled, not the optimal, but the best among our sample set, and pick that as the trajectory that we want to follow to execute our lane change in this case. So this is a simulator video. It looks like a video game because we built it with a video game engine. This is one of the projects that students do as part of the Udacity self-driving car program. Students are controlling the black car here, and what you can see is there's this green string of pearls in front of the car. That's the trajectory that students have to build in order to move this car through traffic. So students are predicting where the other cars on the road are going to go, then they are deciding what behavior, whether to turn or shift lanes left, shift lanes right, speed up, slow down, what behavior is right for their vehicle, and then they have to build a trajectory by building out this string of pearls or waypoints. Those are points that the car has to drive through at any given time step. And this is essentially how highway driving works. Again, it gets much more complex in urban driving, but this is one of the really neat things I think that we've done at Udacity is we've built out about half a dozen simulators like this for different projects that students get to use in order to simulate autonomous vehicles and what development in those is like. And this is, in fact, what a lot of self-driving car engineers do is a lot of work in simulation to build out algorithms that you then test on the car on the road. So the final step in the autonomous vehicle stack is control. And this is how we actually turn the steering wheel and hit the accelerator and hit the brake in order to move the vehicle along the trajectory that we planned in the path planning phase. So we have a trajectory, but now we need to follow it. This is another one of our simulators, and what you can see here is a car driving around a racetrack, and there's a yellow line in front of the car, and that yellow line is the target trajectory that the vehicle wants to follow, or that the student is supposed to code their vehicle to follow. And then the green line is the trajectory that the vehicle is actually going to drive through based on the control algorithm that the student has built. And the goal for the student is to build a controller such that the green line overlaps the yellow line completely, 100%. And of course, you can see it doesn't. This is an area where computers are really, really good. If you want them to follow a trajectory exactly, computers are getting better and better at this every day, and this is an area where things work really well. The harder part is figuring out what to do, but once we know what we want to do, then actually getting the car to execute that trajectory is something that automotive engineers more or less solved. So the final step, in fact, is one of the easier steps of actually getting the car to turn the steering wheel or hit the accelerator, the brake, to move the car through the world. So that's how self-driving cars work. That's how Carla works. We start with sensors, so things like camera, LiDAR, radar, GPS. We use that sensor data to do perception, to actually perceive what's going on in the world, to detect lanes and traffic lights and traffic signs and free space around the vehicle. We localize the vehicle with the help of a map. And then once we know what the world around the vehicle looks like and where precisely the vehicle is in that world, the next step is to plan a path through the world. And so we do things like route planning at a global level, and then we predict where other vehicles are going to go, and then we decide what behavior we want. Do we want to turn left or right or speed up or slow down? And then we actually build a trajectory to execute that behavior. And then the final step is control, and there are lots of different control algorithms. There are fairly basic ones like PID control, proportional integral derivative control. There are more sophisticated control algorithms like model predictive control that build models of the vehicle and model precisely what the vehicle will do if you turn the steering wheel or hit the throttle or hit the brake. But ultimately, this is how Carla works, and this is how most self-driving cars work, is starting with sensors, going through the perception and localization layer, doing planning, and then ultimately having a controller move the vehicle along the target trajectory. So this is our self-driving car. This is my colleague Stephen Welch. He's running student code on the car on our test track. It's coming up to a traffic light, and it's going to stop at the red light, more or less, and then it's going to proceed along a route. And we have students all around the world build code together in teams in the Ukraine, in the US, in Asia. They send us code and we run it on Carla in California, just like this. We do this every week. And we'll hear from Stephen as he finishes up the loop here.
And that's the end of the waypoints that we have set up. Well done. So the car did everything it was supposed to. It drove forward, stopped for the traffic light, continued around following waypoints. Great work.
So it's kind of amazing that, that students anywhere in the world, in Europe, in China, in India, in the United States, in South America and Africa, in the Middle East, can work together in teams. Each team is about 5 students. They run their code in a simulator. They build their code using a simulator that we send them. Then they send the code to us. We test their code again in the simulator to make sure it works. And once everything works for sure, then we put it on the car, and students anywhere in the world can actually write code that goes on a real self-driving car in California. We think that's one of the really special things that we've done at Udacity to help students all around the world learn how autonomous vehicles work and become autonomous vehicle engineers. The program covers the entire autonomous vehicle stack. We start with an introduction. We cover deep learning. We teach that together with our partners at NVIDIA, which is a graphics chip company that does a lot of the graphics chips that train deep neural networks, and also Uber ATG, which has a fantastic self-driving car unit. We teach more traditional computer vision using things like color spaces and lines and edges. We teach sensor fusion together with the team at Mercedes-Benz, their radar and LiDAR sensor fusion team. We teach localization again with Mercedes-Benz. How do we figure out where our vehicle is in the world? Planning with Mercedes-Benz. We teach control with the folks at Uber. And then the final module is system integration, where students bring together everything they learned and put their code on a real self-driving car in California. So that is how Carla, our self-driving car, works. That's how the self-driving car nanodegree program at Udacity works. And it's been a real delight for me to work on that, and also a delight for me to get to come here and talk with you a little bit about self-driving cars. So I'll wind up there. I don't know how much time we have for questions, or if people have any questions, or if we're just moving straight on to our next speaker. But it's been delightful. Thank you very much.
We actually have about 15 minutes for questions or Q&A. So, yeah, please go ahead.
Yeah, please. That's a great question. So the question is, do all the sensors we have on the car check the quality of the road, or do we not have to do that because we drive only in Silicon Valley? So the sensors do check the quality of the road. A lot of the road quality actually gets picked up in the mapping phase. So the thing we do before we actually ever drive the car is we map the area that the car will be driving, and then the car drives through that area with reference to the map. And things like road quality actually make a really big difference to the map. So Sebastian Thrun, who I mentioned, who started Udacity and also started the Google self-driving car project, he would talk about how when Google self-driving cars were getting started and driving up and down the highway in California, they would have to rebuild the map of our local highway in California about every 3 months, because every night, the California Department of Transportation is out on the highway repaving part of the road. And over the course of about 3 months, the entire 100-kilometer stretch of highway around Mountain View, California, would completely change because of all the paving done to improve the road. And so things like road quality affect mapping a lot, and in fact that's why mapping, or an important reason why mapping is such an expensive and difficult part of the self-driving car process, is keeping those maps up to date winds up requiring a lot of work, and you have to keep them up to date, otherwise the vehicle's lasers won't be able to localize to the map, because the map is going to look different than the actual world looks like. Now that said, when the car is driving through the world, if it sees a big pothole that, say, is not on the map, that's where the behavior planning phase is going to come in, and the car is going to have to figure out, is it safe for me to drive over this pothole, or do I need to route myself around the pothole and maybe even shift lanes to get around? And that's one of the more advanced types of behavior planning. So our self-driving car, Carla, actually is not that advanced. It wouldn't see a pothole and decide to move around it. It would see a pothole and maybe decide to come to a complete stop, and then a human would have to take over and drive around the pothole. But some of the more advanced self-driving cars out in the world right now are in fact doing things like that, and that is one of the big challenges of training a self-driving car is getting them to recognize all sorts of things like road quality and figuring out when it's safe to proceed and when they need to turn around or move around an obstruction in the road. And I think your question also points to a kind of interesting fact about self-driving cars, which is they've started and to some extent are still mainly located in cities like Phoenix, Arizona, Las Vegas, Nevada, Silicon Valley, and some of the reasons that self-driving cars started in these areas are Las Vegas and Phoenix in particular are flat. The roads are very well paved, they are very wide, they are rectilinear, and they are fairly easy to drive in. And one of the challenges of autonomous vehicles is how quickly can they move from relatively well-structured environments like Phoenix or Las Vegas and into more difficult places to drive. So a lot of European cities have narrower roads, more difficult to drive. Even cities on the east coast of the US, there are some self-driving cars starting in cities like Boston and Pittsburgh. Those are more challenging environments to drive in, both because the roads are more difficult and also because the weather is more difficult. So there are a lot of different things going on there, but the sensors do ultimately have to get trained to pick up things like road quality, and then the car has to be trained to figure out what to do about different quality in the roads. Great question. Yeah.
Please,
thank you.
yeah, please use the microphone. Thank you.
First of all, thank you very much for bringing all of these bits and pieces of autonomous driving all together and explaining, you know, in a very, very like accessible way of how the autonomous car is actually working. I have like two things, one comment and one question. Comment is related to your test pilot video. I wouldn't be that sure about the quality of a student's code, so just consider buy some helmet or casque for the test pilot. Second question, really. Some people say that well, the future of autonomous driving is not about isolated autonomous driving, but something what other people call the cooperative driving, when not the single car is actually taking decision, but the group of the cars that on the road is actually taking the decision to maximize their the traffic parameters of the whole overall flow. Are you actually working in this direction? Do you think that this is like a good addition to your program?
Yeah, that's a great question. It touches on what are sometimes called connected vehicles. There's a whole acronym called CASE, Connected, Autonomous, Shared, Electric Vehicles. Those are like the big four things. And connected vehicles, really, really important. So our program actually does not touch on connected vehicles. Most self-driving car companies at the moment are building purely autonomous vehicles, and they're not depending on the vehicle to be connected either to infrastructure or other vehicles on the road. But there is a fair amount of work being done on the future of connected vehicles. A lot of people think, I tend to think it's probably about 5 to 10 years beyond the first self-driving cars is the point at which we'll have vehicles talking to each other. Some of the challenges are that in order for vehicles to talk to each other effectively, there needs to be a pretty dense network of vehicles, or all different cars from different manufacturers have to be able to talk to each other. And right now, different cars from different manufacturers, they don't talk to each other so well. In fact, most cars from the same manufacturer don't talk to each other so well. But over time, we think most people think that will probably converge, and you may see things like, imagine a world where the light turns green and all the cars go at once, right? Like now, the light turns green and I sit there and I wait for the person ahead of me to go, and he waits for the person ahead of him to go, and it takes, a long time. You can imagine a world where everybody just moves together because all the cars are talking to each other. There's a pretty lively debate in that community right now as to the exact ways that the cars should talk to each other. Should they talk to each other directly through what's called a mesh network, where one car is talking directly to the other, or should they talk to each other through the internet, where you go up to the internet and then come down to the other cars? There's some basic work being done by Cadillac, which is a GM brand, where if one Cadillac comes to a really hard stop, it will broadcast to all the other Cadillacs within about 400 meters that's happened, so that they know that there may maybe some sort of accident or something to watch out for. But it's really early days on that front. And most self-driving car companies are designing their vehicles for the world kind of as it exists and not a connected world that we hope will exist in the future. But it does seem like 5-10 years from now that may become a lot more common, both vehicles talking to each other and then vehicles talking to infrastructure, talking to traffic lights or hearing when the light is going to turn red. There's also been some interesting work done in talking to traffic signs. A lot of the localization problems we have with maps could potentially be solved by traffic signs that have markers on them that say I'm at this precise location, so if you see me, you know exactly where you are because you know where I, the traffic sign, am. There are all sorts of different things that could be done both with infrastructure and other cars and communication between them. It's a great question. Yeah.
Hi, David. You mentioned the density map which LiDAR is using. Can you expand a bit more of how the map is made and other technologies which enables car to drive without this map?
Yeah, great question. These high-definition maps are typically made by mapping companies. So I think the folks from here are here and going to talk with us later. And it's there's a lot of complexity, in particular, in how you tie pieces of the map together. So in fact, when we did our run from Mountain View to San Francisco, we ultimately wound up paying a specialty mapping company to build the map for us. We built the initial pieces of the map ourselves, but we had difficulty in tying together all the different scans that are required over a 50-kilometer run. Getting those different LiDAR scans all aligned to each other, particularly when the road starts to go up or down, change elevation, change topography, it becomes a fairly difficult mathematical skill, and the maps also take up a lot of space, and so working with that becomes kind of a big data problem in tying together all of this data. So there are specialty mapping companies. Here is one, TomTom is another. Google has their own mapping unit. They have maps both for kind of the Google Maps type of maps that you and I use on our phones, and they have different maps for the self-driving car maps that Waymo needs. And these maps are becoming kind of a competitive advantage for different companies that have access to them, because keeping these maps up to date for the reasons I was mentioning earlier about road construction, utility construction in cities becomes a big problem. Keeping these maps up to date becomes really hard, and getting access to them is difficult. So one of the things that people are working on is fleet mapping. So you can imagine if you have a fleet of self-driving cars, say several hundred self-driving cars driving around, they may be able to map the city as they drive and feed that data up to the cloud, and then you can have servers in the cloud that are actually combining all that fleet data together and keeping the map up to date in real time. Most self-driving car companies don't have enough vehicles on the road right now to really do effective fleet mapping, but that's kind of the dream of where this might go. There are also efforts related to something called SLAM, Simultaneous Localization and Mapping. I think we're going to hear in a few hours one of the other speakers talk about SLAM. So SLAM is this technique where you build a map as you drive through an area that you've never seen before, and you can actually kind of analogize this to how you and I might drive a car. You and I can drive a car in a place that we've never seen before, and we kind of figure out as we go, what does that look like? It's a little harder to drive somewhere that we've never been before than to drive somewhere that we've been 100 times, because if we've been somewhere 100 times, we have a mental model. We've essentially built a map in our heads of what that area looks like, whereas if we've never been somewhere before, we kind of build the map in our heads as we drive. That is more or less at an analogous level what's going on with SLAM. And there are companies that are working on being able to send self-driving cars into areas where they've never been before by doing things like SLAM, or maybe even doing SLAM with just camera data. Most of the mapping work that's being done right now is being done with LiDAR, with arrays of lasers. There are companies, Tesla is kind of the poster company in this field that are doing most of their work with camera data and figuring out how to do what's called visual SLAM or visual localization is an even harder problem than just building a map out of LiDAR data. So it's kind of an open problem, and it's something a lot of companies are working on. It's a research problem. The kind of state of the art right now is to build these high definition maps. That's what most self-driving car companies rely on. But the future may be either in something like fleet mapping or in something like SLAM, where vehicles eventually are able to drive even somewhere where they don't have a map. Yeah. Yeah, Sergey, so what hardware do we use in processing and what? How do we meet real-time processing requirements? Yeah, that's a great question. So we use actually fairly basic off-the-shelf hardware in Carla, and that's again because Carla is a bit more of a simple self-driving car. It's not like a Waymo level driving through the city self-driving car. It works for our educational purposes. And so what we have in Carla is a high-end Linux gaming machine essentially in the trunk with an Intel i7 processor, an NVIDIA Titan X GPU, 32 gigs of RAM. And then actually the most expensive computer in Carla is not our main computer, but it's the little box, comes from a company called Udacity that connects what are called the twist commands, essentially the vehicle commands that we send from Carla. The Udacity box converts those into signals that the car's internal network can understand. So we have to know how to talk to the Ford car that we're driving, and in fact there's another company that specializes in how to convert those signals into signals that Fords can network, their control area network, the vehicle's internal network can understand. And then on top of that, of course, we have all the sensors that I mentioned. For higher-end self-driving cars, there are a slew of companies, everybody from NVIDIA to Intel to Renesas, that are building automotive supercomputers. So NVIDIA has their Drive PX series. Their latest version is the Drive PX Pegasus. If you look at it online, it's this kind of symmetrical computer, symmetry and redundancy, really important for automotive because if you essentially want two systems. If one fails, you want to be able to fail over to the other system. There are all sorts of considerations both in the speed of the computer and also in making it what's called automotive grade so that it can withstand the rigors of being in an automobile and all the motion issues that come along with that and the heat issues and the lifespan issues that come along with that. Our motherboard has already failed once in 2 years just being in Carla in the trunk of a car. And so companies are working really hard to make really fast automotive supercomputers. And kind of the leading edge of that is Tesla. Tesla's latest earnings call, their Q2 financial call was kind of interesting because they said this, they were talking all about their numbers and their revenue and building the Model 3, but they said this really interesting thing in the earnings call, which is that they are now essentially building their own computer. They design their own ASICs chips, and Tesla, of course, is not a level 4 self-driving vehicle. They are an advanced driver assistance system right now, their autopilot system, but they have essentially designed their own chips that they're manufacturing specifically for Tesla that are going in the trunk of their car, and essentially what they're doing is it seems like they are training their deep neural networks. They're doing most of their work with camera images and deep learning, training their deep neural networks outside of the vehicle, which is what anybody would do. But then once they know what kind of deep neural network they want to use, they're building chips specifically optimized for the deep neural network that they've trained so that they can run really, really fast inside the vehicle. They've even made some allusions to, over time, swapping out the computer in the vehicle. So you might buy a Tesla this year, and in 2 or 3 years, they might say, come back to the Tesla dealership and we're going to give you a new computer to put in the car that's more optimized for the new deep neural networks we've trained in 3 years from now. So there's a lot of interesting work being done in the hardware area. Our hardware in Carla is fairly basic, but you can get some really sophisticated, really expensive, really high performance automotive computers for production level vehicles.
Thank you.
Hello? May I? So it's always a pleasure to see how someone telling a story which he really likes. So thank you for this. And my question is about costs of HD maps. It's really huge, and basically, car producers would like to not be dependent on providers of navigation maps, right? And they're trying to introduce some kind of unified standards for this. At the same time, I believe that future of HD maps and is when car itself, so cars on the market itself build and keep the map valid and actual. But this means, on the other hand, that if I'm driving here cars, for example, I can improve here maps only. So do you believe in some kind of common standard of HD maps in the future?
Yeah, great question. So if we have lots of different mapping companies, will they develop a common standard for their maps, or will each company have its own proprietary standards? I have to say that's a business question that I probably actually have less insight into. I haven't thought deeply about it. My sense is, at the moment, maps are a real competitive advantage for the companies that have access to them. And so I don't think there's necessarily a lot of motivation for the mapping companies to share data with each other. That may change. I would also be interested to hear from the folks at here when they speak later today. They could probably give you an even better answer than I could. But I think it's possible that over time, as we see companies form different alliances, those alliances and partnerships may involve sharing things like map data across companies. So we've seen a tremendous number of partnerships form just in the self-driving car space between companies like Daimler and Bosch, between companies like BMW and Intel and Fiat Chrysler. And you can imagine these alliances starting to come together to affect mapping companies. In fact, here is largely owned by the German Big Three, which is an instance of another instance of kind of partnerships touching mapping. Over time, if one dominant mapping company really emerges as kind of the owner of maps in an area, you can imagine other companies kind of deciding to partner together more closely to try and catch up to that company. The technological ability of companies to do fleet mapping may also affect this. If companies are able to build out fleets and build their maps from fleets of vehicles, then there may be less need for different companies to partner together. I think it's kind of an interesting business question that is maybe affected by technology, but is probably actually a little more affected by business and strategy of the companies involved.
Hi, thank you for your presentation. I have a question about improper behavior of other driver in our cities. So how you learn about this improper behavior? How you teach your algorithm? How you manage this situation? Do you collect this data? Do you do something with this?
Yeah, great question. So human drivers often do not obey the law, and that's a challenge for self-driving cars. In fact, a lot of drivers in areas where self-driving cars are being tested get frustrated because the cars will follow the speed limit exactly, and following a car that is not exceeding the speed limit can sometimes be a frustrating experience. Whether cars are trained themselves to violate traffic laws in the same way that humans routinely violate traffic laws is really right now a decision that's being made by the automotive companies involved. It seems like over time that will be a question that gets raised to the level of lawmakers and automotive regulators. Right now that they're only on the order of tens or in the case of some of the larger companies, maybe hundreds of self-driving cars in any one location, which is just a tiny fraction of all the vehicles that are in any given city. And so it's become less of an issue, but as self-driving cars become more prevalent, I think regulators are going to start to get involved along with ethicists in dictating to automotive companies exactly how self-driving cars should behave. Perhaps an example, a very basic example is a lot of us have cars with cruise control. I have a car with cruise control. That's a very basic form of driver assistance. And in fact, I can set my cruise control to violate the speed limit, right? Like I can set my cruise control to go at 140 kilometers an hour if I wanted. That's something the automotive companies have permitted me as a driver to do. You take it a step further, will the automotive companies permit their self-driving cars without any input from the human to actually drive at 140 kilometers an hour? That's a bit more of an open question. And then, of course, how do they react to other vehicles driving that fast? To get back to your original question, reacting to other vehicles that are violating the law is actually a bit of an easier question, because that's just a matter of prediction. So how do we predict other vehicles on the road are going to behave? We may know that one possibility is that a car may violate the law. In fact, this is something that comes up all the time. Waymo has all sorts of crazy videos. Sebastian, my boss from his days at the Google self-driving car project, has tons of videos of cars driving the wrong way down the highway or driving straight through a red light. Those are just things that as self-driving car designers, we have to program our vehicles to be able to handle, because we can't depend on human drivers following the law all the time. We have to be able to predict that they may in fact violate the law. The harder question then becomes, do we drive more like humans, or do we drive more like perfect law-abiding citizens? At the moment, I think most vehicle operators are driving more like law-abiding citizens, but that may become a frustration point in the future, because a lot of our laws are almost designed to be violated. That's something that for politicians and regulators and ethicists to help us think through. The engineers will essentially do what the ethicists and the regulators tell us to do on that front. I think that's it. It's been a delight to speak with you, and I'll be around if you have any questions about self-driving cars. I love talking about them, so please come and find me, and I'm excited to hear our next speaker.
Thank you very much, David.